we discussed 3 ways of solving constraints: analytical, procedural, and numerical. This video will look at examples of procedural and numerical approaches to solving constraints. Area ratios are often used in city planning to control density. 2 common measures are floor area ratios and building coverage ratios. Floor area ratio is the ratio of a total floor area to the area of the site. Building coverage ratio is the ratio of footprint area to the area of the site. In the diagram, we see a series of examples of massing options with differing ratios. In this example, the constraint that we will tackle is the floor area ratio constraint. We will start by using the procedural approach. This approach defines a sequence of steps that allow the constraint to be solved. For example, let's say a site has a floor area ratio of 4. Then the permissible floor area that can be constructed on the site would be 4 times that site area. Often, with such constraints, designers will explore alternative massing options that achieve the floor area in different ways. In this video, we have an urban block with plots around the perimeter and with an open center. We assume that the maximum floor area of the block as a whole is fixed. We then use the procedural approach to generate building massing options on the plots. These options should get close to the maximum floor area, but they should never exceed it. For this example, we are not trying to match the floor area exactly. This is because we are always duplicating whole floors. In the diagram we can see 3 examples of massing options. The task is to generate a set of building massings with randomized varying heights but constant total floor area. In this simplified example, we will look at just 3 buildings. The total combined area of all the buildings is required to be a maximum of 15,500 meters squared. In this case, the heights are assigned in a randomized way. The challenge is to find a way to ensure that, for any randomized heights, the total floor area will remain constant. A procedure is defined to achieve this, consisting of 6 steps. The first step is to assign a set of relative height values. These can be values in any range. Here we use values between 0 and 1. The heights are relative to one another. So if one building has a relative height of 0.45, then it is higher than another building with a relative height of 0.32. These numbers can be assigned according to some other rules, or can be generated randomly. In the second step, the area of each plot is calculated. In the third step, the relative area of each building is calculated by multiplying the relative height by the plot area. The resulting relative areas again only have meaning in relation to one another. In the fourth step, the percentage area is calculated. This is the percentage of the target required area, which in this case is 15,500 meters squared. First, the total of all relative areas is calculated. Let's call that the total relative area. For each plot, the percentage area is calculated as the plot relative area divided by the total relative area. In step 5, the number of floors for each plot is calculated. The total floor area is calculated by multiplying the target area by the plot percentage. The number of floors is then calculated by dividing the total area by the plot area. The resulting number is rounded downwards, since for the number of floors, an integer is required. For this we use the floor function. Flooring means that the total floor area will always be lower than the maximum. Finally, in step 6, the buildings are extruded. We will now look at 2 extensions to this scenario, where additional constraints are applied. The first additional constraint is to set a minimum number of floors. And the second is to set a maximum number of floors. The current procedure can result in some plots having no buildings, and other plots having excessively tall buildings. A second constraint can now be added. The constraint can specify the minimum number of floors. The diagram depicts the case where the minimum number of floors is set to 4. This means that, even if the relative height is 0, the number of floors will still be 4. This will also bring down the height of the tallest buildings. In order to solve this constraint, the target floor area is first split into 2 parts. The first part is the base area, which will remain constant. In this case, it is 4 times the footprint area of the lots, which comes to 9,000 meters squared. The second part is the remainder of the target area, which we call the upper area. This will be 6,500 meters squared. The same procedure can now be applied as was used previously. Relative heights can be assigned and the number of floors calculated in the same way. The key difference is that instead of generating buildings to fulfill the target area, we instead focus only on the upper area. A third constraint can now be added to the procedure. This constraint will limit the maximum number of floors. However, solving this constraint is more difficult. So far, we have used a procedural approach to find solutions to the constraints. In this case, a numerical approach will be required. The numerical approach uses a solver to search for solutions to more complex constraints. We will use a very simple solver to search for solutions that satisfy all the constraints. For this, we will use a generate and test type of solver. The third constraint limits the maximum number of floors. This means that the number of floors must vary between the 2 constraints, the minimum number of floors and the maximum number of floors. For any buildings that exceed the maximum, the floor area needs to be redistributed to the other buildings. In order to solve this constraint, a trial and error process is used. The process keeps reducing the heights of the tallest buildings until all buildings satisfy both the minimum and maximum height limits. The progressive reduction in building heights is achieved by gradually increasing the values for all relative heights. In the diagram, 3 iterations are depicted. Each iteration increases the relative height by a value of 0.1. The first iteration sets the relative heights to 0.0, 0.7, and 0.0. The second iteration sets them to 0.1, 0.8, and 0.1. And the third iteration to 0.2, 0.9, and 0.2. Increasing all relative heights in this way means that the actual height of the middle building will keep getting shorter. Here, the diagram shows the percentages of total floor area. In the first iteration, the middle building had 100% of the floor area. In iteration 2, this reduced to 80%. In iteration 3, it reduced to 70%. The process is repeated until the height of the tallest building comes in under the maximum building height constraint. The final model now has 3 different constraints that are automatically satisfied: the total target floor area, the minimum number of floors, and the maximum number of floors. Finally, there is one additional thing worth highlighting with regards to constraints. This is that constraints can conflict. The diagram depicts such a case. The maximum number of floors constraint is set to 2. And the total target floor area constraint is set 15,500 meters squared. In this case, it is impossible to satisfy both constraints. In such a case, one option is to give an error message so that the user is aware of the problem. Or alternatively, one can prioritize one constraint over another. Previously, we discussed 3 ways of solving constraints. So far, we have looked at examples of analytical and procedural approaches to solving constraints. For the last constraint, we also looked at a simple example of the numerical approach. In the next videos, we will look at more complex examples of the numerical approach.